I'm the last presenter for this session, and my name is Liang from LinkedIn. So today, I'm going to talk a little bit about how we optimize for the careers job marketplace at LinkedIn through doing some application redistribution work. So this is a LinkedIn job homepage. If you go to www.linkedin.com, there's a jobs tab where we recommend the good jobs for you based on your profile and your past activities. So how it works? So in a high level, it works this way. So suppose you have a member, which is me. You have, we look at the title, we look at education, we look at skills, we look at everything on your profile, which is public. And on the other side, we also look at the jobs, and we are trying to do a good matching and determine the relevance score. Finally, able to match these good jobs, find good jobs, and recommend them to our members. So one thing to note is that this is actually an entire job marketplace, which is what we are running, meaning that there are a lot of job posters who posted this job, and the members come to the site and trying to apply for the job. And job posters will receive the application, and end of day decide whether this user is fit for the job, qualified for the job, so that they can further interview, or they just simply say that maybe next time. So we are actually running a marketplace here. So historically, the ranking algorithm that we have about job matching is mainly optimizing for user engagement. So what does that mean? That means that we are simply modeling we rank the jobs and model the responses by looking at the probability of a member apply for a job, given a member is shown with a job, right? So that means that we only care about the member engagement side without worrying about the job poster happiness side, right? And we have been building a lot of models, comprehensive models, trying to predict the probability of the member applying for a job in a very accurate way, right? So if you have been to the deep learning tutorial that we have given on Sunday, that one mostly is focused on, we have a case study there which mostly focused on this part, right? However, this is not the complete picture. And the complete picture is actually, we want to recommend the most relevant jobs to our users, while we ensure that each job posting receive sufficient number of applications at the end of the day, right? Because if we don't do that, if a job poster come to our site and pay several $100s and receive 0 application at the end of the day, they are not going to be happy, right? And most likely they may not even renew our contract with us. So there's going to be a net loss on job poster value, happiness, and also LinkedIn revenue. So we want to avoid that as much as possible. So on the other hand, one question we often ask our job posters is, what happens if you receive, let's say, 1,000 applications or 10,000 applications? Do you feel happy? The answer is also no, meaning that it takes them actually extensively long time for them to interview, and it's a lot of effort they consider. So they won't be happy if they receive too many applications either. So now, we did some analysis, and basically we look at the probability. Y-axis here is the probability of there is a confirmed hire from a pool of candidates who apply to the job. And X-axis here is the total number of applications for a job, right? And you can see that it's actually a diminishing return from job poster perspective. So the first time that you receive the first application, usually the return is very high, right? Finally, you got the application. That's great, right? But at the time that when you receive, let's say 5 to 10 to 100 to 200 to 1,000, finally, even the incremental values start becoming 0 or even negative, because they start feeling that maybe I should withdraw this job because most likely there are already people in it. I don't want to interview anymore. So that is why we want to come up with an approach that we are able to redistribute the job in a way so that we want to make sure a job does not receive too many or too few applications at the end of the day, right? And in the meantime, we want to be able to make sure the relevance of the site still remains the same, which looks like very challenging, right? So the question is, how do you do that? That is going to be the focus of the talk. So the high-level idea is actually quite simple. We call it early intervention. What does that mean? So suppose a job expires at some time, let's say capital T. Let's say it can be 30 days, right? And at any time, Let's say maybe 5 days. You have run this job already for 5 days. You have 25 days left. And we start looking at the data about how many applications, how many impressions, what the CTR this job has already received, and also combine it with other features. And then what do we do is that then we want to somehow try to predict accurately about when we, given the data we have received up to now, we look at beyond, like at 30 days, and we try to predict how many applications the job is going to receive at the end of the day, right? So suppose we find out that it's going to be too few based on our confidence, then we're going to start boosting the ranking score, which is mainly driven by the relevance, right? On the other hand, suppose we feel that it's going to be too many, maybe 1,000 or 100, then we're going to start penalizing the ranking score early, right? So that it doesn't happen. So otherwise, we will prefer not to intervene at all. Let the engagement model to actually drive the whole optimization. So that is a high-level idea. So now here's a key question, right? It looks like we need some oracle model, right, which are able to tell you that at day 5 that what is going to happen in day 30, which is why we need to build a model, right? So I'm going to start spending some of the slides, future slides, to talk about how we are going to build a model that we can accurately predict the number of applications that a job is going to receive at the end of the day. So first of all, what are the signals that we can use, right? We can use, of course, we can use the number of applies and impressions a job has received so far, right? That is most likely the most useful signal that we can have. On the other hand, what happens if you have a cold start on day 1, right? You don't have anything. Then what do? Then that means that you can still do something. And also, there are also some seasonality, for example, features such as time of day or day of week that we can use, right? I mean, the cold start part comes from the job attributes, right? Maybe different title, different company may have different, patterns of how they receive impressions or applications for the 30 days of period. So that's the feature that we can also leverage. So that is a high-level idea. So let's start talking a little bit about how we build the forecast model of job applications. So here I'm going to start using some mathematical notation. So let's assume CJT is the applications that a job received for job J at time t, okay? So now, from the beginning of the time to the end, we want to predict the number of clicks, a number of applies, which is CJ1 to t. And up to time small t, actually we all reserve the data, right? So that is actually a constant. We will not need to worry about that. What we need to worry about is actually the second term, right? Which is J t plus 1 to big T. So that is why you can easily write down, okay, so the expected value of the and variance is actually simply just the second term. That's what we need to care about. So how do we forecast the second term in the formula? We forecast the second term of the formula by a product of the apply rate, which is mu, notated mu, and also impressions that we anticipate is going to receive, right? So here we are making somehow a little bit strong assumption that mu and v are independent, right? Which simplifies a lot in terms of our prediction. So now the question is, what is the model for mu and what is the model for v? And once we are able to build a statistical model for mu and v, then we should be able to have a mean and variance estimate for C, which is the number of applications that we want to do. Right? That is a high-level idea. Okay, so apply rate mu JT. I think this is something that I'm simply borrowing of a lot from the previous papers done by Deepak Gawal and also Mike West. I mean, people have done a lot of work in terms of how to predict the CTR in the real time, right? And the idea is very simple, right? You do a gamma boson model where you have a prior that has a gamma prior and at time t, and you have a boson model which is simply modeling the relationship between the number of applies and the number of impressions, based on the CTR rate. And then what happens is that at time t, you can compute the posterior based on data you observed and also the prior knowledge that you have before time t, right? And you can basically set the posterior to also be the same as to be the prior for the next batch, right? So which is very, very, very trivial and has been a lot of work that has done in this area. So now you have the model for the apply rate, and what about the impressions, right? For impressions, you can actually do very similar things, but the mathematical computation is a little bit it's a bit less straightforward, but still can be done in closed form. So the idea here is that you can have a baseline model which use the features that I mentioned about the job attributes, right? And on the other side, you also have a per job adjustment that are able to, based on the number of impressions the job has received so far, you can actually adjust further on the baseline model. And you can basically first learn the feature-based baseline model, assuming there's no adjustment. Every job is the same. And then after that, you can simply assign, when the new job comes, you can assign there's a prior, and then you just updating the posterior in real time based on data you have received. So now, up to now, so that the job adjustment lambda j start to become not equal to 1 and learn more and more as you receive more and more data. And you can actually even integrate the lambda j out, make it to be a marginal prediction model, meaning that based on the number of impressions you have received so far, how many impressions you're going to receive in the future, which is actually a negative binomial distribution by integrate out the rate of the Boltzmann model. So these are some mathematical details. I think and then once you have the applied rate and also the impression forecast, what you can do is simply again by assuming that they are independent. Now you just simply do the expected value and variance by doing the multiplier of the two. So just following the mathematics, and finally you are able to get to the 95% confidence interval of the number of applies of applications a job will receive at the end of the day. Okay? So that is basically what we want to achieve by doing this. So what we want to achieve by doing this is that at the end of the day, given what I have observed so far, and now I have the confidence interval of the job, number of applications the job is going to receive at the expiration time. Right? We have the lower bound, which is L, and the upper bound, which is U. Now what do we do? So you have the confidence interval, okay? Now, what you can do is actually very straightforward now. Suppose the lower bound of the number of applications is greater than something which you don't want to happen, right? So 100, for example. So that means that when the job receives more than 100 applications, the people may start complaining to you. The job poster may start complaining to you. So that is why we say, okay, maybe when the lower bound is greater than 100, this is when we need to intervene, right? Because we strongly believe, we have 95% confidence interval, strongly believe that we're going to start, the job is going to start over-delivering, right? That is why we start penalizing the ranking score, right? How do we penalize? We use a simple exponential decay by, making the ranking score to times the exponential to the minus of proportional to the number of applications the job has received so far. So the more applications you have received so far, the more we are going to penalize. And divide by some softness, which is a tuning parameter that I will show the impact later on. And on the other hand, we also want to do some boosting, right? So suppose the upper bound of the applications at the end of the day is going to be less than some threshold, let's say 8, right? So that means that we strongly believe in 30 days the job is going to definitely under-deliver, right? So that's that's why we may want to boost. However, the trick here is that we don't want to boost blindly, right? We only want to boost the jobs that are good, right? Because if the job is really bad, then you may say that I don't want to do it, right? So that means that we want to put some threshold on the relevance score as well, right? So make sure that we don't just simply boost any random jobs that cause some issues, right? And that is why there's a threshold of the relevance score that we can tune as well. And finally, when you decide to boost, what do you boost? Again, you can see that we're trying to play it conservatively, not like the penalization, we are doing it more aggressively. Here, we just simply do it with a constant factor because we don't want to boost it too much, right? So now we have talked about the modeling part. Now let's talk about the system architecture part a little bit. So how are we going to build the system so that we're able to do it, right? So this includes both the original system and also the new added-on components. So in a high level, what happens is that you have user who with the user data, and we have workflow to compute the all the models that we have, including both the relevance model and also this statistical forecasting model. And we basically push the model to our online model store that basically stores all the models that we have. And we also have the user feature store that stores all the features. And we also and what happens in the real time is when the user comes and they are going to start query our relevant system and then ranking system, and then it is going to first retrieve all the candidates that are good and then ranked by the relevance model, right? And then what happens is that we do need to further adjust the score, like what we just talked about, using the statistical model about that is basically decided whether to penalize or boost. So that's why we have a stat server first to collect in real time refreshed every few minutes about how many applications, how many impressions this job has received so far, and then started doing the forecasting about what is going to happen when job expires, and finally decide to boost or penalize and put this as a re-ranking step of the jobs recommended by the original relevance model. Okay, so that is a high-level overview of the system architecture. So what about our experimental results? I'm going to quickly go over it. So first of all, I want to show you some insights about why some certain features in your model is very useful. So you can see that here we show that across the total number of days, starting from the job get posted to the job get expired, the number of applications and impressions we receive every day. So what you can observe here is interesting. So there's a strong job freshness pattern, meaning that first of all, system feels that for the fresh jobs we want to show more. So system basically favors the fresh jobs than the non-fresh jobs. And also there's a weekly pattern as well, right? So this basically shows that if we are not careful, we will end up with not be able to predict the impressions or application accurately without using these features, right? So that's why it's become a very important feature in the impression prediction model, right? Actually, I forgot to mention one thing. For the apply rate model, you can also do the same thing by introducing the feature-based baseline model as how we do in the impression prediction model. Actually, we did that in the paper, but just here for simplicity, I skipped that part. So our offline evaluation strategy is actually not so complicated. So the idea here is, again, is about determining whether we're able to make the right decision at a certain time, right? So basically the idea is, suppose at time small t, suppose our decision is to penalize or boost, the question is that decision correct, right? And what you can do is simply looking at what actually happened at the end of the day, right? And then become a binary classification problem, right? So basically, you can say that, I look at this, I'm going to evaluate using like a traditional how we evaluate the binary classification models, saying that suppose, we boost the job correctly, right? Then it is a positive label. Suppose we decide to penalize the job correctly, it is also a positive label. On the other hand, suppose we made the wrong decision at the end of the day, then it becomes negative label of my binary classification. That is how we do test, and so that we can start generating AUC curves for whether we're able to make the right decision at any time, right? So that is why you see that at day 3, the performance of AUC is the worst, right? Because we don't have enough information at that point. We are just simply guessing based on the features. And then these gradually AUC curves become better and better, and then finally it becomes really, really good at the date of 25. Day 25, which means that we most likely we already know what is going to happen, right? Make sense? For both penalizing and boosting. So we also did this in our online A/B test from September to December 2016, where our control is basically, let's just simply optimize for the user engagement only. And the treatment is basically, let's do this and see what happens, right? And to better analyze what has happened, we split our jobs every day into 3 buckets. So bucket 1 is the jobs that are in danger, means that up to now, it has not received enough number of applications. And bucket 3 is actually up to now, it's already received more than 100 applications. That means that we should stop showing any application to this, receive any application for these jobs. Or ideally, but actually practically it won't happen because we still need to guarantee the user engagement out there. And bucket 2 are the jobs that are in the normal range that we care less about this problem. So you can clearly see that from this table, we have tried 3 methods, right? One is the boosting only, one penalizing only, and also the third one is the boosting plus penalization. And clearly the boosting plus penalizing works the best. So I want to highlight 2 things. So first of all, if you look at the application percentage change in the bucket 3 and versus bucket 1, we're actually able to redistribute a lot of clicks. Basically, this part become negative. We're able to redistribute the application from bucket 3 to bucket 1, which is exactly what we want, right? Because we don't want further application to be received in bucket 3. However, we want more and more application to be received in bucket 1 because this is where we really care about. Second one I want to highlight is that the user engagement in this experiment actually is neutral. Okay, so that means that we are actually not hurting engagement by doing this, which is exactly what we want. And third thing I want to highlight is that before and after, we actually look at the entropy of the number of applications a job receives. And entropy actually increased by 12%, which means that we're able to redistribute the number of applications the job received by week of week is actually much better. Although this is not a statistical test, but accuracy, but this is at least something that we want to make sure it happened. So the last one is I want to show you some impact of the tuning parameters that we have, such as the softness parameter and the threshold and boost factor. What does it do, right? So we also did multiple A/B tests in our online framework, trying to evaluate the performance of this impact of these parameters. And you can clearly see for sometimes it does generate a big difference. For example, for the boosting parameter, right? The more you boost, actually sometimes it suddenly makes the bucket 1 performance to become much better, but it may end up with sometimes hurting the performance, global performance, when you boost it too much. So I think I'm over time now. I want to quickly conclude. So in this paper, we have talked about a system that we're able to redistribute the job applications to make the marketplace healthier while without impacting the engagement too much. And one of the important future work we are doing is that we are trying to put qualified applicants into this framework, because we believe that just simply looking at the application is not enough, but actually the qualified applicants is what job posts really care about. So we are building a qualified applicant model which fits well to this framework. Thank you.